Okay, here is going to be my attempt to explain what I was trying to explain last class period. I should probably be studying right now, but whatever. Anyway, this is a little thing I made in Fun, the physics simulator I often use during class. And essentially what it is, it's a scale like we were discussing in class, the first case, where the objects are directly in line with the pivot point of the scale's arms. So if you can see here, the scale itself is this purple bit, and I'm going to go and rotate it a little bit so you can see it a little better. Hold on, I got to run the simulator first. Okay. So you'll see right here we have these purple arms and these green masses. So the purple arm is the actual radius, because in this case the radius passes through the arm because it's the path between the mass and the center of the arm. All right, and same on the other side. So we discussed ways to solve this kind of problem, to find the torque being exerted by each mass, and using the second method was using the force times the perpendicular component of the radius. So like originally we were doing the perpendicular component of the force times the whole radius. Now we're doing the whole force times the perpendicular component of the radius. So I tried to approximate the perpendicular component of radius using these springs. And because force of the weight these guys are applying, the force they're applying to the rod is weight, and that force always points directly down, the perpendicular component of the radius will be just the horizontal component, kind of like the x direction, the projection of the radius on into the in the x direction. So as you can see here, this spring represents the horizontal component of each radius, and then the little red arrows represents the force. So watch what happens when I rotate this. As I rotate it up this way, I gotta run the simulator again. Okay, the horizontal component of radius on the right will shrink, as will the one on the left. And the forces remain the same, of course, because the objects aren't getting any heavier or lighter. So what's happening is the torque is decreasing on each side as I rotate. I can go through the center and go away, because as we said, torque is going to be the perpendicular component of radius times the force, and if the radius drops, the torque also drops. So the take-home message here is that the torque drops the same on both sides. So no matter where you are, you have the same amount of torque. So this thing has no tendency to settle out to be flat. It will just continue to spin however it likes. And that's not good, because you want your scale to kind of like do something like this, where when you have it unbalanced, it'll kind of like wobble back and forth until it's balanced. So that means this scale is not very good. It's not the ideal scale that we want to use. So I also created this guy over here, which is our ideal scale. And this is kind of what I was trying to go for in class. So this scale is shaped so that it has a centered. It has a rod going down like this, attached to an arm like this at a 90-degree angle, and it's fixed in place. This is not a pivot point. This is a solid solid point, so this will not swivel or anything. So in this case, the radius is not this as it was in the first case. The pivot point is up here. So the radius is actually this way, and likewise over here this way, which is represented by these two springs. And the horizontal component of the radius will be represented by this spring and this spring right here. So once again, as I was saying earlier, we're going to find the horizontal component of this radius here and multiply it by this force. And then the horizontal component of this radius here multiplied by, the horizontal component of this radius, which is right here, multiplied by the force here. So the key difference between the last model and the current model is what happens when you rotate. So I'm going to run the simulator. Oh, that's wobbling too hard. And I'm going to demonstrate the incredible trig problem we were trying to accomplish in class. And as I rotate this, you'll see, like if I tip the left side up here, the horizontal component of radius on the left will get longer as the horizontal component on the right gets shorter. And likewise, if I go the other way, watch very carefully what happens. That happens. So, and I can probably run it kind of slowly if I'm careful, and you'll see that happening. So what's actually happening here is as one side gets higher, its radius, its effective radius, the perpendicular component of its radius, or the horizontal component of radius, gets longer. So the higher object has a longer radius, and the lower object has a shorter radius. The masses are still the same, so the forces they're applying are still the same, but the lengths are changing. So as we know, the formula for torque is the perpendicular component of force times distance, or in this case, the force times the perpendicular component of distance. I hate saying that word. I've said it like 100 times. Anyway, as the distance becomes shorter, the torque will also become smaller. So, and likewise, as the distance becomes longer, the torque will become greater. So as you can see, the side that's higher up will have a greater torque because it has a greater distance. And same with the other side. So anyway, I hope that cleared up some stuff. If it didn't, I can demonstrate it again in class. And that's about all I have for you guys. So thanks for listening, and I'll see you guys next week.